All right, our next speaker this afternoon is Joseph McDonald, who has joined us from Stanford University. Joseph has been working this summer with Dan, and he's going to tell us about their project together, deciphering the information content of spectral energy distributions.
All right, thank you, Gwen, for that introduction, and thank you to everyone else who's joining us here today and joining via Zoom. Let's get into it. So a little bit behind the motivation behind this project. So astronomers today are still trying to answer the same questions or similar questions as they were 100 years ago. Some of these include where and when were the heavier elements in our universe created, what did the early universe look like, and how did our galaxy, as well as others, evolve over time. And while these questions are still open, we are pretty confident in the fact that answers will come from knowing the most we can about the star formation histories of galaxies. So over here on the right, we have a plot from a 1985 publication from Carnegie's very own Sandage, showing the different star formation histories based on different galaxy morphologies. And we can see some pretty cool patterns, star formation histories that die off immediately, and others on the bottom of the plot that actually increase over time. So this plot is just to show that we've known the answers to these questions are related to these star formation histories for quite some time. As a brief introduction to the project itself, so physics works in one direction only. Galaxies create stars. Here we have these star formation histories for 10 different galaxies. So they make these stars emit light, and then we're able to observe this light and display it in the form of, say, a spectral energy distribution. So we have a very solid understanding of how this works from a physics standpoint. From an astronomical point of view, though, we want to see how much information we can infer from this observational data about the star formation histories of these galaxies. So many think we'll find the answers to questions on the previous slide by collecting more and better data, different kinds of data. And while this is certainly important, it remains unquantified exactly how much information is truly present in these observational type of data that we make. Which brings us to the project itself. At the start of the summer, we were working with pretty simple synthetic data. We created these fake star formation histories using Gaussian distributions. There's an example of two of these on the right. And I was just looking for patterns between the spectra and the star formation histories, trying to gain some intuition into how changing the star formation history would change the spectra. Overall, it was a pretty simple exercise in gaining intuition into how changing a star formation history affects the redness or the blueness or the brightness of these galaxies. And then after that, we moved on to working with more realistic data, still synthetic data, but here we have the first 6 star formation histories from this set we're working with, and immediately you can see the resolution is a lot higher, and they look a lot more like more realistic star formation histories. And additionally, there's even in just these first 6, there's some pretty strong diversity amongst them. Then we can visualize these star formation histories in another way. Here, each of these rows is representative of an individual galaxy. The red are the areas where there was more star forming activity. The blue is where there was less. And you might be able to see these little specks of green where the star formation history was really, really high. So we're actually working with this list of over 19,000 of these star formation histories, and plotting it like this, we can begin to see some patterns in the data, mainly that for most of these galaxies, their star forming was done earlier in their lifespan rather than later. And then additionally, just some more specifics about this data we're working with. So once again, it's synthetic data, and everything is very, very idealized. So we're working with these E-mile spectral energy distributions for single stellar populations ranging in ages from 30 million years to 14 gigayears. We made the choice to not include anything for dust attenuation or reddening, simply because we're after the information content of these spectra themselves and not anything that relates to dust or reddening. Additionally, all these models are at a fixed solar metallicity and for quiescent galaxies, meaning they're non-star forming. And lastly, we're focusing specifically on this range of wavelengths from 2500 to 8950. Last thing about this data, here we have a plot showing the mass accumulation history for the first 10 of these galaxies in our data set. And as we can see, there's some pretty serious diversity in the star formation histories. Like this blue galaxy, for example, accumulated all of its mass very early in its lifespan, and then didn't get much more as time went on. And these other galaxies obviously show different patterns in their evolution. But despite this diversity, the spectra of these respective galaxies all look very similar. So this leads us to the two main questions we were dealing with this summer. One, how can we differentiate between these different spectra, even though their star formation histories look completely different? And once again, how can we begin to quantify the amount of information that's truly present in this kind of data? And the method we chose to go about this was matrix factorization, specifically a type of matrix factorization called singular value decomposition. If we can look at this plot on the bottom left, this is a subset of 1,000 of those initial galaxies that we were working with, transformed into their spectral forms. And this is actually the set of data that we plug into our process of singular value decomposition. So we take this matrix and we decompose it into 3 additional matrices, U, W, and V. As you can see, U and W are very dim. There's not a lot of information. We're pretty unconcerned with its contents. V, on the other hand, is very bright, lots of information. Essentially, V contains the information content of these spectra that we put in the form of these orthonormal eigenvectors. Here we can see the first 6 of these eigenvectors that we extract from this process of singular value decomposition. And immediately we can notice some pretty cool patterns. First of all, this first eigenvector looks like the spectrum of a very old star. It looks like the spectra of the data we're working with. Additionally, the second eigenvector, as well as the 4th and 6th, show features that we would find in very hot stars. There are also noticeable Balmer lines, and the calcium K line is a particularly prominent feature for this set of eigenvectors. So now that we've extracted these eigenvectors, we move on to this process of training and testing. So for training, we take a subset of this data, like the 1,000 we were working with. We perform singular value decomposition, extracting the eigenvectors from them. And then we want to perform some testing. We want to see how well these eigenvectors can recreate the set of another set of spectra. So here we have the first 10 spectra in this subset of 1,000 we're working with. And below that, we can see the residual error when we do this process of recreation with 5 eigenvectors. We get some pretty substantial error more towards the blue, which levels off as we get further in the range of wavelengths. And then when we do this exact same process only with 10 eigenvectors, we can see the error decreases drastically by a factor of 10, in fact. So then the question becomes, how many of these eigenvectors do we need specifically to be however accurate? Once again, these are the first 6 from that set we extracted. And now in the top right, we have the RMS of the fractional residual error shown, and how that number decreases as we implement this recreation process with each additional eigenvector. So for this first one, when we do the recreation process with only 1 eigenvector, we get an error of 18.73%. What this means is that over 80% of the original information content is preserved in this 1 eigenvector alone. And then when we do the process with the first 2, it decreases to 10, and so on, getting all the way down to less than 1% when we use 6 eigenvectors. So this brings us to the major conclusions and findings we found. On average, for this specific data we're working with at these specific wavelengths, it's all very idealized. We found that you need an average of 10 eigenvectors for an average accuracy of 99.9%. And additionally, you only need 6 eigenvectors for an average accuracy of 99%. Also, we found that these templates for spectral energy distribution fitting are highly compressible. So we started with this list of over 19,000, and we're able to reduce that to just 6 or 10 individual numbers, which, if nothing else, this will drastically reduce the processing time needed when working with large data sets, may be able to speed up complex simulations. Yeah. So then last thing, some of the next steps we're considering doing. lots of cool games we can play. First, we want to hopefully repeat this process this time with real data. It's important to note, though, that when we do this with actual data, it's likely these observations will have a signal-to-noise ratio of anywhere from 30 to 50, which means it's unlikely we'll need any more than 4 or 5 eigenvectors, simply because beyond that, their impact in the recreation process is actually less than the noise itself. So it would just be useless to gather those. And then the thing I'm most interested in is actually relating the eigenvectors themselves back to the spectra themselves, or the star formation histories themselves. So as we saw in the eigenvectors earlier, there's that really prominent calcium K line. And we want to know how that shows up in the star formation history itself. So a lot of cool next steps we can do, cool games we can play with this data. Thank you everyone for listening. Any questions?
All right, questions for Joseph?
This is really interesting, thank you. So my question is about the different wavelength ranges. So if I could, this may be a more observer-oriented question, assuming that maybe you only can observe part of the wavelength space, given this study, which part would you suggest would be the most informative part? Yeah,
that's a really great question. It's hard to put a strict number to which part exactly is the most important. If I had to take an educated guess, so here once again we see the residuals when we're doing this process of recreation, and the most noticeable error we get is in this range of closer to blue, more like towards the UV. So I'm thinking if we expanded our wavelength more into the UV, that could potentially hold a little more information, simply because there's more diversity in the data here. So yeah. Not particularly. We've added all these constraints to this set of data, and it's likely there are just some outliers, more so in this area with the specific data we're working with. But yeah.
Other questions for Joseph?
I had a question about the physical interpretation of the eigenvectors. Was there anything in particular that stood out to you, or any physical, like physics, that could potentially motivate that set of observables as eigenvectors and not others?
I'm sorry, I'm a little confused by your question. Could you restate it possibly?
On maybe the slide before this, I think you showed that a lot of these eigenvectors corresponded, okay, maybe a couple back, to physical, like this, to physical observables, right? Like the calcium K line. I wonder if you have a sense of any physics behind that would make, say, the calcium K line be an eigenvector, but not a different calcium line or a different element line. I don't know, this isn't a trick question.
Yeah, no, that's a really great question. And that's really what we want to start looking at more in the future. Like you said, this calcium K line is super prominent, but we simply don't know yet how it results in the star formation history.
Other questions?
So in this graph, what are you plot? I mean, I know you're plotting the eigenvectors, but what is your y and x axis like against, like what parameters does that contain?
So when it comes to these eigenvectors, the actual axis things are pretty unimportant. We're able to scale and stretch these eigenvectors however much we want. So it doesn't really matter. It's pretty arbitrary. But if we're looking at it in this physical sort of context, this would be wavelength in angstroms, and this would be spectral power in whatever form.
All right, let's thank Joseph.